Mic off.
Okay, can you all see this?
Mic on.
Yep.
See a black screen?
Yeah.
Okay.
With the PowerPoint.
Yeah. Okay.
Mic off.
All right, so let's cover a few announcements. Okay, the upcoming labs will have number 20 and 21 posted next week. And then this week's lab, which was 19, will be due Monday. And see, exam 3's today, it's due tonight by midnight. So far, I have one exam sent about 3 o'clock. So I had an early finisher. So I'm expecting all the rest sometime before midnight. And we have a quiz coming up that will be next Wednesday, the 22nd. And that will cover the first part of chapter 21. And regarding the schedule, we were supposed to do the chapters in order, like 19 before 21, but it works out better to switch them around a little bit, like go back and forth. So tonight we'll start off with 21 and then maybe switch back to 19 and back and forth through the end of the semester. And 21 is about nuclear chemistry. So that's what we'll be going over tonight, just the basics though. Tonight will be a little shorter than usual. So I'm sure you'd rather spend time working on the exam.
Mic on.
And the intro for chapter 21 isn't that long. Question?
No, not a question. Just I've been working on the exam for 5 hours. It's been quite a bit.
Oh, it's a head scratcher, huh?
Yeah, it's still not as much time as the last one took, but it's been slow going.
Okay.
Mic off.
Well, thermo is rather complicated. And then, electrochemistry is one of the more difficult chapters. Well, if it's any consolation, the upcoming chapters are a little easier. Okay, here's nuclear chemistry, chapter 21. Okay, nuclear chemistry is ultimately about radiation, and especially when it's associated with nuclear decay. And radiation is energy which is transmitted through space as electromagnetic waves or energetic particles. And the usual Roy G. Biv spectra that we're familiar with, where it goes through all the colors of the rainbow, that's also electromagnetic radiation, but it fits into a very narrow part of the overall spectrum. And this graph here shows the tiny piece of the overall spectrum that visible light fits into, visible light being composed of all the colors of the rainbow. So if we look at the x-axis on this graph, it's in powers of 10, and the powers increase as we go to the right, and the units are frequency. So as we increase the frequency of the wave, we raise the energy. So energy increases from left to right. So if we start at the visible spectrum and go to the right, that is toward higher energy, and we go from violet light to UV light and then to X-rays and gamma rays. And UV light has a higher energy than violet light. UV light's responsible for suntans. It reacts with the chemicals in our skin and darkens them. And so if we go to still higher energy, we go to X-rays, and X-rays being used for medical issues with bones. And before their harmful effects were known, X-rays were used in shoe stores. The salesman would have an X-ray machine there, and to show how well the shoe fit, the person would would try it on, and then they would put their foot in the X-ray machine, and then they'd watch the bones in their feet and how well it fit into the shoe. So that was fairly common in the early 1900s before the harmful effects were known. So now we know better, and especially with gamma rays, that's even higher energy. Gamma rays are so high energy that they can penetrate thin sheets of lead. It takes a layer of lead, at least around a centimeter thick or so, to stop gamma rays. And if we go towards lower energy, we start at red and go to the left, that is towards lower energy. Then we go to infrared light, and then to microwaves, TV, and radio. And the lower energy, even like I mentioned, microwaves, it's like microwave oven or a cell phone. It's one of the reasons you don't want to have a cell phone in contact with your skin, because the manufacturers don't recommend that, because a microwave induces what's called a spin transition, and molecules with dipole moments, especially water. Water has a large dipole moment, and microwaves can cause it to spin, and it has 3 possible directions it can spin. And so chemicals that possess such features like that can be induced to spin like a water molecule, and when they spin, they bounce around into one another, and it sort of mimics the effect of infrared radiation, that is heat. So in a microwave, the water molecules bounce together, and if you go up and shake it after it's been microwaved, you notice often it'll boil instantly. It's because it changes from spinning like a top to bouncing around like a regular heated molecule. So it's why the manufacturers of cell phones advise to not carry them next to your skin, or have them they advise to keep them in airplane mode when sleeping next to them and stuff like that. Okay, there are several radiation types we deal with typically. First is alpha, and they're denoted by the Greek letters or alphabet. It's from the words alpha and beta hooked together. So the symbol for alpha, A, in Greek is this fish symbol, and then the beta looks a lot like our B, and gamma is a G in Greek. So we use those Greek symbols to denote these different forms of radiation. And a neutron is just denoted by the letter N. And this chart here shows their penetrating power. An alpha particle, which has it's composed of 4 nuclear particles. There are 2 neutrons and 2 protons, but it has no electrons. So it's like a helium atom with both electrons removed. Now, an alpha particle can't even penetrate a piece of paper. So it's a large thing. It's a fairly sizable molecule. So we wouldn't really expect it to be able to penetrate into a solid very far. And not only that, but its charge, it has a +2 charge. So that charge will also cause it to repel and keep it from penetrating very far. A beta particle is an electron. So a beta particle can penetrate paper, but it's stopped by like a thin layer of foil, like metal foil, like aluminum foil would stop a beta particle. And gamma has a much higher energy. And like I said, it takes a lead sheet to stop gamma radiation. And a neutron is the most penetrating form of radiation. It's the actual piece of a nucleus that's kicked out as a result of a nuclear reaction. And a neutron has no charge, and it's also extremely tiny. It's the size of a proton, and it can pretty much go wherever it pleases whenever it hits a solid, and it takes like a few feet of concrete to stop a neutron. So let's go through each type in more detail. An alpha particle comes from a nucleus. Like here, this picture shows what's called the parent nucleus. It's U-235. It's an isotope of uranium. And one of the characteristics of uranium is that it spontaneously decays into other elements. And it does that because its nucleus is unstable. And there is a lot of uranium in the Earth's core, and it's one of the sources of radon gas that we hear that home builders are concerned about at times. Like, you check out the ground you live on to make sure there's not an excess of radon, but it comes from the uranium. So in this diagram, it shows U-235 ejecting an alpha particle. And if we do the math, subtract out an alpha particle that has 2 protons and 2 neutrons from the however many neutrons and protons it had initially, we would end up with thorium-231. So the thorium-231 plus the alpha particle make up the original parent U-235 molecule. And this alpha particle has little penetrating power. Like we showed earlier, paper can stop it. Now, the next particle that's typically emitted is beta. Beta is an electron. And here's an example showing how a beta particle could be generated. In this case, it's by the potassium-40 isotope. So its nucleus spontaneously changes. It emits the beta particle and changes itself into calcium-40. And it also emits an antineutrino. And one way that radiation is commonly measured is with a Geiger counter. And that's why if we pass a Geiger counter over our hands and our bodies, it will set off the Geiger counter. And that's because the potassium in our bodies spontaneously emits beta particles. And a beta particle can easily go through paper, but a sheet of plastic would stop it. So the next particle, well, it's not really a particle, but it's actually a form of energy. It's gamma radiation. And an example of that would be cobalt-60 spontaneously emitting a gamma radiation plus a beta particle and becoming itself its daughter, the nickel-60 isotope. And gamma radiation is something we want to stay away from for sure. It can easily go through paper or plastic, and it takes a lead sheet to stop it. And the other one we mentioned was neutrons, and being uncharged, it can easily go through paper, plastic, or lead, and it takes like 3 feet of concrete typically to stop neutrons. So all of these particles are spontaneously emitted by certain elements in the periodic table, and it's mostly at the bottom in the rare earths, like the lanthanides and actinides. They're large nuclei. Many of them are unstable. Some are man-made, and they spontaneously want to become a different element. So they kick out these alpha, beta particles and gamma radiation to achieve their goal, which is to become something more stable. And the level that this occurs is measured in what's called the half-life. And it's very similar to the half-life that we've done in the beginning of the course when we reviewed first order, second order chemical reactions. It's measured the same way. We keep track of the number of particles emitted and note that they decrease over time. And in a certain length of time, we'll have half of what was there initially, and that amount of time is referred to as the half-life. And different isotopes have different half-lives. They can vary all over the place. Some are measured in years, like here, hydrogen-3 has a half-life of 12 years. Carbon-14, which is used to date plant matter and things like that, has a half-life of 5,730 years. Phosphorus has, or in the case of P32, 14 days, P33, 25 days, and sulfur 35 is 88 days, iodine 60 days. These isotopes that have half-lives on order of days are the ones that are typically useful medically, because we can use these isotopes to treat tumors. We'll go over that a little bit later. But they're not, the reason we would want a half-life of roughly days is so that they go away. Like if they're put in a body, that they do their task, which is to release their radiation, and then they disappear. Their half-lives run out, and essentially they just dwindle away to nothing. If they had a half-life that was shorter, like milliseconds, that'd be too short. If it was years, it'd be too long. But when it's around days, it's just about right. So let's look at a half-life calculation. Well, first, though, let's go back a bit here. Here's class notes on nuclear chemistry. By the way, this layout will change a little bit. I'll be rewriting this as we go along in the next week or so. And so it'll roughly be the same, but some parts will look a little different. So here is a typical question, like name the 3 common types of radiation emitted during nuclear decay, and list them in order of increasing ability to penetrate and ionize material. So for penetrability, what would be the least penetrating form of radiation? Does anyone know?
Would that be like alpha particles, or would it be like microwaves?
Yes. Yes.
Okay.
Yeah. The least penetrating would be alpha. How about the highest?
Be like, would it be gamma rays, or do you want the type of particle?
Gamma rays is fine. It's a type of radiation.
Okay.
And in the middle would be beta. Now, with respect to ionizing power,
mic off,
which would be let's say, what would be the most ionizing of those 3 types? How about
Mic
Diana? Are
on.
you out there?
Which one would be the most ionizing out of what? 3?
Out of alpha, beta, and gamma.
Gamma?
Well, that's a good first answer, although ionizing power requires that whatever it is would have to be charged. Like if two atoms, like if one atom ionizes another, that atom itself has to become charged. Like when the particle passes through material, it has to attract charge to itself. Or that's what the term ionizing power means.
So would the most ionizing one would that be an alpha particle because it's
Right,
just
yeah,
like
because
protons basically, protons and
yeah,
neutrons?
it's the most charged. It has a 2+ charge, so it would be the highest.
And then
Okay, what would the medium be?
would that be the beta particles again?
Right,
And then
yeah, and the least would be alpha. Or not alpha, the least would be gamma.
so like penetrability and ionizing power are like opposites. So the more
Right, yeah,
penetrability you have, the lower ionizing power.
right, yep. Yeah, like a
Mic
neutron, we
off.
didn't talk about that, but that would have even higher penetrability, but its ionizing power would be like next to nothing. Okay, now let's look at the next question. A daughter of radon and how it causes health problems. Here is a page from, see, it's a review for a continuing ed exam for a radon technician. If we go down a few pages, like, well, it starts out with things that we've just gone over. Like they talk about alpha, beta, gamma decays. Now that here they show how radon is generated, and it comes from the Earth's crust. U-238 is the most common form of uranium. It has like 97 or so percent abundance, maybe higher, maybe even 99. But U-238 spontaneously changes into thorium-234 and several others, all the way to radium, and then finally here to radon-222. So here's radon-222. It comes from radium-226, which, by the way, emits out an alpha particle and has a half-life of 1,600 years. So the radium hangs around for a long time, but once it generates radon has a half-life of only 3.8 days, and it spontaneously ejects an alpha particle and becomes polonium-218, which in turn ejects an alpha particle, has a half-life of only 3 minutes, and becomes lead-214, which in turn ejects another alpha particle, half-life 3 minutes, becomes bismuth-214. Then, and so it goes on for another couple steps and ends up finally as the stable lead-210 isotope. So if we check out radon, like the things it does all the way until its stability is reached, see it ejects one alpha particle here, another here. Here it's beta and gamma, then beta and gamma, and then alpha. So it emits all three types of radiation, all within a fairly short half-life. So radon, by the way, is one of the noble gases. And chemically, it's stable in the sense it doesn't chemically react with other things, but its nucleus is unstable. So it's a short-lived element, and it's of concern because of all these forms of radiation that it emits. Now, radon is mostly a concern deep in the earth, and I'm pretty sure it's in South African diamond mines where the workers were turning up with lung issues that resembled the black lung from the coal mines there of the early 1900s, when dust would get in coal miners' lungs to the point where it would accumulate. And anyway, autopsies on miners in South Africa showed that the radon caused blockages in lungs similar to those of the coal miners in the early 1900s. And then since then, we've learned that this decay process is what's going on. So the radon could be breathed in, and then it goes through its transitions and deposits lead then in the lungs. So in some places in the country, we're concerned about radium, and it's kind of rare, but it depends on like where the concrete is bought from that's used to construct a home. Like if it's shipped in from some other part of the country or from overseas, then it could have a higher than usual concentration of radium or radon. And so it's happened in the past actually that like out east, a subdivision was actually constructed and it was found that the concrete contained too much radon, and it was a big problem. But most of the time it's usually reserved to deep in the earth, like in the South African diamond mines. Now, as far as measuring radiation and comparing to the different types, let's see, somewhere in here. Yeah, here it is. Yeah, here is a table that compares the typical dosage measured in millisieverts per year for the different forms of radiation that we're all typically exposed to. The cosmic rays is only 0.27 millisieverts per year. Ground radiation, 0.28. Nuclear power is only 0.01. And diagnostic X-rays, nuclear medicine's 0.53, but radon is at 2. So it's quite a bit higher than the other forms of radiation. And this table uses units of millisieverts per year, but a more common unit is millirems. REMS, REM. So it's the equivalent unit would be millirems per year. And here's a table of recommended dose limits for the various parts of the body. And skin, it's recommended like 15 rems per year. A hand, 75 rems per year. Forearms, 30 rems per year. Body organs, 15 per year. And then there are dosage differences depending on if a woman's pregnant, for instance, 0.5 rems during gestation periods. Students, 0.1 rem. Any individual in the population, 0.5 rem. I'm not sure why there would be a difference for students and an individual in the population. But there must be some reason it's written that way. And to keep track of this, normally a dosimeter is worn. So a little radiation sensitive tag that's worn. And you see them like in a doctor's office when they're doing x-rays. The technician will typically wear this. It's like around their neck or it's clipped to their pocket. And it's sent in periodically to measure how many REMs have been absorbed. And there's only a certain amount that's allowed. So once the tag is registering too many REMs, then that person isn't supposed to be doing any more x-rays. Okay, so now as far as the different isotopes, like there are a lot of different isotopes. There's an interactive periodic table that's put out by the Radiochemistry Society. And this forms the basis of radiomedicine, which I think is probably one of the most up and like has a really high growth potential in the field of medicine, so using isotopes to treat medical conditions. But anyway, if we have a look at this periodic table, it looks just like any other interactive periodic table, but if we click on an element, like gallium, for instance, it shows us the usual info like symbol, atomic number, and weight, but also tells us how many isotopes it has, how many are radioactive. Like this one has 38 total isotopes, of which 29 are radioactive. Only 2 are stable. Shows the typical energies that it emits. And then we can click here to view all the different isotopes. So here's a list showing gallium 56, 57, 58, all the way down to gallium 74. So gallium, see, its atomic number is 31. So the first isotope has what, 25 neutrons. The next one has 26, 27, 28, 29, and so forth. So these isotopes differ only in the number of neutrons. And this decay mode shows the type of radiation it emits. Like here, beta plus is a positron emission. It's an electron with it's kind of like the antiparticle of an electron. It's like an electron, but with a positive charge. Here, beta minus is what we've been calling beta emission. And there are some other types, but get the idea that, yeah, there are a lot of radioactive isotopes. We can check out a different element, like something bigger. You can see if gold has many. Wow, looks like there are quite a few gold isotopes. And most of them emit positrons. Here are a bunch of beta emitters. Here's four or five alpha emitters. Okay, so for each of these isotopes, they have their own half-life. So let's look at half-life here. Here's an example, like relating a half-life to something that's every day. Let's suppose that your body mass is 100 pounds and that half of you disappears each week. So in other words, your half-life would be 1 week. How much time is needed for your mass to equal 1 pound? Well, to figure that out, we can make a list This is a long way to do it. So we'd start with 100 pounds, cut it in half to yield 50 pounds. That would be 1 week elapsed. Then we take the 50 pounds, cut it in half. It's another week, and we go on down the list. Just keep going and going until we reach a pound. So it looks like we get to a pound roughly. Here it's 0.78 pounds. And that took 7 weeks total. So this is a long way to find this out. Could try a different way. It's a little easier, which is to construct a table. So we just have a table of 100, then 50, and all the way down to when it drops below a pound, and then increment the weeks on the side, and we end up with somewhere between 6 and 7 weeks. So this is a little bit more precise, but there's still a better way. So let's do this the exact way. Let's use logs. You notice if we take 100 and divide it by 2 over and over again, that's the same as dividing by 2 to the nth power. So what we're trying to find out is 100 on 2 to the nth equals 1 pound. We need to find out the value of n. So let's solve for n, and because this involves an exponent, logs are the natural choice. So we can solve this for n. We take the log of both sides. We get n as the log of 100 on 1 divided by log 2. And we get n as 6.64. So our answer exactly is 6.64 half-lives. And that would be weeks in this example. Does anyone have questions?
Mic
If
on.
not, we'll just continue.
Mic off.
Let's see, this just basically shows all the steps of the algebra that was done. That was to solve for n. So we ended up with n as 6.64 weeks. Okay, radiotherapy, we'll hit that a little later. But let's go back to these class notes and go towards the bottom. Yeah, examples of half-life calculations. And this goes over another few examples. Here is the half-life of a given isotope is 10 years. And if we start with 10 grams of it, how much is left after 20 years? So we can make a table to do this fairly quickly. So we start out with elapsed time in one column and the amount remaining in the other. So at 0 time, we have the full 10 grams. Then after 10 years, which is 1 half-life, we cut the 10 grams in half to get 5 grams. Then after 20 years, that would be another half-life, so we cut the 5 grams to 2.5. So the amount remaining would be 2.5 grams. Another example is if we start with 12 grams, and after 11 years, we find that only 3 grams is left. What is the half-life? So we could find this out in a similar way. We construct our table with elapsed time versus the amount remaining. So we started with 12 grams, and we just keep cutting it in half until we get to the 3 grams that was given in the question, and just keep track of the half-lives. So it went through 2 complete half-lives. 2 half-lives must then be equal to 11 years. So we take our 11 years divided by 2 half-lives, and that gives us 5.5 years per half-life. Here's an example relating to how we date fossils. That's using the carbon-14 isotope that has a half-life of over 5,000 years. So what's done is the amount of isotope that's in the fossil is compared to what's out and about in the current day, and we find out what the difference is in this case, this bone contained only 1/4 of the usual amount of radioactivity. So if it contained only 1/4, we can make a table like we just did of elapsed time versus amount remaining, but this time it'd be percent instead of grams. So we start with 100% and cut it to 50, cut it to 25, which is the level that the bone had, which means it went through 2 full half-lives. So the age of the bone would have to be 2 half-lives, each of which is 5,760 years. And that gives us the age of the bone, which is 11,520 years. Okay, these others are about brachytherapy. Let's have a look at this slide. Okay, here's an X-ray showing a normal lung on the patient's right side versus a lung with tumor on their left side. And let's look at a way that it could be treated, which would be radiation therapy. Here's a diagram showing 2 ways that it could be treated. The first would be on the right, external radiation. An external beam could be focused on the tumor, and that would definitely tear down the tumor, but it would also affect the healthy tissue around it. A better way would be to put the source of radiation at the site of the tumor, and we could do that with radiation seeds. And the seeds would be composed of some radioactive isotope, and they would be implanted at the site of the tumor. And ideally, the half-life would be something like a month or so that it would do its job and then dwindle away and not cause any harm to healthy tissue. So here's a drawing showing how this would be done for a lung. A bronchoscope would be inserted into the trachea all the way down to the tumor site, and a catheter would deposit the radioactive source at the site of the tumor. So let's look at an example of this. Let's suppose that 1 milligram of chromium-51, whose half-life is 28 days, how much time is necessary for it to decompose to 1.5 grams? 1.5 micrograms. So we're starting with 1 milligram, ending at 1.5 micrograms. So this shows the basic way of doing it, which would be to construct a table to give an approximate answer. So we would end up with about 10 half-lives this way, which would be 280 days. And if you know anyone who has radiation therapy of some kind or another, or implanted seeds, they'll tell people like not to hold a baby in their lap at the beginning, because there's like up there at the top of this table where quite a bit of the pellet remains. So they're hot. Like it's not only hitting the tumor, but the radiation goes in other directions as well. And so it could affect somebody who's up really close, like someone who's like a baby sitting in someone's lap. So that would be the reason for that instruction. And it takes, like this table shows, around 280 days in this case for it to dwindle down to where it wouldn't be harmful to anyone else, or including the patient. So let's solve this using logs. The problem we're solving is we have an initial mass of 1,000 micrograms. We're cutting it by a factor of 2 n times until it's 1.5 micrograms. So what is the value of n? So let's solve for n. We get n is log 667, which that's 1,000 divided by 1.5. And that, so the log of 667 is divided by log of 2. The 2 comes from here. It's the base of n. So now that gives us n is 9.38. So 9.38 half-lives, which is 263 days. So that it gives us a more exact answer compared to the table. Here's another example. Okay, this time let's find out how much chromium-51 should be used. In the last example, it was given. It was 1,000 micrograms. This time it's not known, but we do know it needs to decompose to 5 micrograms in 1 year. So let's set that up by first calculating the number of half-lives. And so the half-life is 28 days. So in 1 year, there are 13 half-lives, which is taking 365 and dividing by 28. So we get 13 half-lives. Okay, and to do this like a table, we are working backwards. So you'd end up with something like this. We're doubling the amount. 5 is what we're ending up with. So we're working backwards. So we double the amount each time. So we go from 5 to 10 to 20 to 40 until we do that 13 times, and we get 40,960 micrograms. So that's the long way. Not really recommended when we can do a log calculation pretty easily with a calculator, but this way it comes up with 41 milligrams. So let's calculate it. Here, the top of this fraction is unknown. That's our x. We're cutting it in half n times and ending up with 5 micrograms. So let's solve for x. So we know what n is. N's the number of half-lives, which is 13. So solve for x. X is 5 micrograms times 2 to the 13th power, which is 8192. And we end up with 40,960 micrograms, or roughly 41 milligrams. So that would be the amount of this radioactive isotope that should be implanted. So let's go back here for a minute. See, in this PDF, we had a brachytherapy example. See, the first one is asking how much time is needed for a 100 milligram pellet of 103 palladium to decay to 1 milligram. 103 palladium is what's used often in, see, I think it's prostate cancer. It has a half-life of only 17 days. So if we follow the solution here, doing the table method, we get 120 days. But if we do this using logs, we set up the formula. We have our initial mass divided by 2 to the nth power is equals our final mass. So that's, let's see, 100 on 2 to the nth equals 1, and the units are milligrams. And go through the math, we end up with 6.64 half-lives. And if we take that and multiply by 17 days per half-life, we get 113 days, which rounds to 110 days. So it's roughly, what, 3.5 or so months is what it would take for the 100 milligram pellet to decay to 1 milligram. Okay, let's look at radon a little more. Oh, I already showed you that. Showed you that. Showed you that. The end. Let's see if there are any other goodies. No. Oh, yeah. Let's see. The textbook is Jesperson, chapter 20, which is on Wiley Plus. We'll be going into more detail on all of this. They have some interesting pictures here of the parent nucleus and the daughter and the particles. I'm not sure why they drew them this way. Our largest element has a nucleus, or has an atomic weight of 200 roughly AMUs, or grams per mole, which means like altogether the number of protons and neutrons should total like roughly 200 or 250. But this ball here has way more than that in it. But it shows the different particles, like here it shows an alpha particle being ejected, and this example shows an electron or beta particle coming off. Here's gamma radiation coming off. This next one's a positron. Next is a neutron. But we'll be following Jesperson in this chapter and also in chapter 19, which is coordination chemistry. Okay. So I'm going to stop the recording. Okay, so it's recording stopped. I'll post that on Blackboard. Okay, does anyone have questions?
Mic on.
Not anything jumping out at me right now.
Okay. How about on the exam? Did anyone have trouble accessing the PDF keys I put up there on Blackboard today?
The keys for the notes?
Yeah.
No, the only thing that I've had trouble accessing is the lecture videos in Microsoft Teams. It always comes up for me that the video is not available or the video can't be found.
Yeah, same here.
But like I have my recordings, so
They're supposed to keep them there for 2 weeks. And when I access them, they work just fine.
they?
I'm not sure why it'd be different.
Okay. Maybe
Well,
I'm
how about
doing something wrong then.
the PowerPoints, like the silent videos?
Those work fine.
Like,
yeah.
oh, okay, good. So
Mhm.
those I think are more useful. They show step by step, like you can control the speed and everything it goes through.
Right.
Although it's missing the explanation.
Yeah. It the no audio PowerPoints are really good.
Okay, all right, I'll just keep posting them then. Okay, well, anything Corona related?
I think the curve is flattening a little bit. If people like would stop protesting over shutdowns.
Yeah, some people, it's getting where some people are really feeling the pinch, like their business could like fail
Mhm.
permanently if they don't get back in.
Yeah. Stimulus checks are getting sent out though. Bunch of people I know got
Oh
theirs.
yeah. At Walmart today, the system crashed, so you could do cash only
Mhm.
because everybody was buying stuff with the stimulus checks,
Yeah.
and everyone was buying like huge TVs and stuff.
That sounds about right.
Oh,
But then, like, the people who had carts full of groceries for their family had to go put everything back because the system crashed. And I thought that sucked.
yeah. Yeah, I've heard that it's causing a problem that small businesses who are told they can't operate, like for instance, a place that sells TVs, they're sitting there watching people who need TVs going to Walmart and getting
Yeah.
them there. It's like, and they're wondering, well, why am I shut down when Walmart's allowed to be open? And it's creating a problem.
Yeah. I definitely wouldn't mind if like Target shut down their non-essential departments, mostly because I work in electronics at Target, so I wouldn't have to go into work. That would be pretty sweet.
Yeah.
You know what? My mom just bought a ton of graduation stuff for me today at Target, even though I don't get to have a graduation or a party.
That's okay. I have one in spirit.
Maybe it's for the day it does happen. Maybe it's just postponed.
Right.
Once it gets too far past it, it's like, what's the point, you know?
Well, Diana, is that still shut down in Florida pretty much?
Yeah, for the most part. I don't know, like, not much for me has changed really. I mean, like, I can't work obviously, but I don't know. Yeah, pretty much everything shut down.
Yeah, I heard the governor there like increase the number of restrictions lately.
Yeah, and then our county, I live in Brevard County, and so Port Canaveral is part of it, and so there's like a whole bunch of issues with the cruise ships and people like being stuck and cruise ships trying to like from other countries trying to dock here because they have like sick people or dead people on board like trying to get help, and so that's been kind of a big deal because they're like getting turned away from everywhere else. Like nobody really wants to deal with it, and they don't want to have to spend the money in like their counties, if that makes sense. So it's kind of been a big deal.
Yeah, it sounds like a pretty tough situation for the cruise ships.
Yeah.
Well, just for comparison, though, I have a diary of a Mississippi riverboat captain from the 1840s, and in it he mentions in the 1840s he was coming down past St. Louis, and he mentioned that a cholera epidemic was going on at the time, and there were over 300 people dying per day, and that they were being brought out to the riverfront near where the arch is, and they had a gigantic funeral pyre. But they were disposing of 300 plus bodies a day there. So that would be like way, way worse than what it is now.
Something tells me that wouldn't really fly, but also wouldn't look too out of place in the middle of the Mississippi River in St. Louis.
In the middle of the Mississippi River?
Crossing over the Mississippi and just looking at the brown water. It's like, yeah, this is a great looking river.
Oh, okay, right, yeah.
Like it wouldn't
That
surprise me to like be crossing the Poplar Street Bridge and being like, yep, there's the giant funeral pyre. The classic
Okay.
St. Louis skyline.
Well, does anyone else have news about Catherine? I think we've lost Catherine. Well,
She's probably working on the exam.
Probably. Okay. Well, good luck on the exam. If questions
but I'm
pop
still
up,
here.
okay. Well, if questions pop up, send email. So I'll be online till around midnight. So, okay. Well, have a good weekend. See you next week.
Me
Yep.
too. Bye.
Bye.
You too.